All right, we're going to actually continue our discussion of sinusoids a little bit. Here we see our familiar green sinusoid from the last video, so we should write it a little bit formally. The green trace, I suppose I should have changed my color to green just to make it more meaningful, but was V of t. We had an amplitude V naught sine omega t. With a radial frequency omega, and we actually did the numbers, so we know V naught was 3 volts, F was 2,000 hertz, and so omega is 2 pi times 2,000 equals 4,000 pi, and we can multiply the pi if you want, 3.14 times 4,000, but I can just leave it like that. Depends how you want to write it. Either way is fine, and that's units radians per second. So mathematically, we can write V of t equals 3 sine 4,000 pi. And again, you could write it as 12,000 and some t, and that wave has units volts. So there's our sinusoidal function expressed mathematically. Our blue trace is a shifted function. So we can add a little bit more to our sinusoidal expression, namely V of t, I'm going to put a little b down there for blue, little subscript, equals some V naught sine omega t plus phi. Phi is a phase term, and specifically we tend to call it a phase shift. So it's a shift in the signal away from a phase of 0. So the green trace has a phase of 0, and it goes through 0 at t equals 0, as I kind of highlighted there, as a sinusoidal signal does. But blue, if I were to continue that blue trace there, changing the color, it would go intersect 0 somewhere over there, or similarly right there, but to be consistent with the sinusoidal signal, off to the left there. So that's been shifted in time, and so that's a phase shift. Phase shift typically can have units in radians, though sometimes you can do it in degrees. You have to be careful, though. Radians is the better choice because omega t has units radians, and if you're going to do this out mathematically, writing phi in radians is better if you're going to use your calculator. Though, as humans, we probably have a better feel for degrees and what that means. So, when we look at this signal, we do notice that the blue peak comes before the green peak. So if I go and just pick 2 peaks, there is our phase shift, V, phase shift. But the blue peak happens before the green peak. And so the phase shift can be either earlier in time or later in time, and that corresponds to sine. So here I wrote omega t plus phi, but phi can be positive or negative. So if phi is negative, the signal shifts to the right later in time. It happens later in time. And then continuing that on to the next page, if phi is positive, it shifts to the left. The signal shifts to the left. Put quotes around left, earlier in time. And so actually looking at our little plot there, the blue signal comes before the green signal, the reference signal. And so it is earlier in time, so we know there's a positive phase shift. Now, I did say we have units radians or units degrees. There, I put little arrows down at the bottom. And we can use either one. But when we're looking at a plot like this, when we want to get our phase shift, we have to do a little bit of mathematics. So this is a sinusoidal signal. One cycle of a sinusoidal signal corresponds to 2 pi radians. We also know it is 1 period. So in other words, 2 pi and a period go hand in hand. We can look at our phase shift, which I'm going to do in radians here. And then we can look at the delta t between the peaks. So going back to our plot, I can look, and I have this written as a phase shift, but practically I can go down here and I can say on the axes, this phase shift corresponds to a difference in time. That's always the case. It always corresponds to a difference in time. So we can correlate our delta t to our phi. So we can get delta t from the plot. Turns out it's about, well, it is 0.1 millisecond because I said it, but if we're eyeballing it, we can use whatever approximation we get. But in this case, delta t, for our example, delta t is 0.1 millisecond. So we can go write that on our plot, equals 0.1 millisecond. So, and we know t from previous work was 0.5 milliseconds. And that means we can get the phase shift by taking these two relationships and writing phi over 2 pi equals delta t over t, or in this case, solving that for phi equals delta t over t times 2 pi, and we get phi equals 0.1 over 0.5, and milliseconds if you want, but they will cancel, times 2 pi. I didn't quite give myself enough room there. And so we can write that as 0.4 pi. So 0.1 over 0.5 is 0.2 times 2, 0.4 pi. There's our phase shift. And again, we can crunch that as a number if we're so inclined, multiply it by pi, get 1.2 something radians. Let's add that. Make sure we have our units, radians. And so overall, mathematically, the blue trace has the same frequency. We know F was 2,000 hertz. We can go back and look at that. And omega is 2 pi times that, and we had already written that out. That's 4,000 pi radians per second. We see it's the same amplitude, so we know the amplitude is 3. And our phase shift now was 0.4 pi down here at the bottom of the page. And so we have V naught as 3 volts, and our phi equals, and I should stress, it's plus 0.4 pi because it was a phase shift to the left. It was earlier in time. And so we will write plus 0.4 pi radians. And overall, we can write V of t blue, little b for blue there, equals 3 sine 4,000 pi times t plus 0.4 pi. So there's our discussion with phase shift. It's kind of a big topic, and we do see phase shifts quite a bit in our circuit analysis. We have one more sinusoidal video we're going to talk about. It's going to be a lot shorter than this one. I'm going to end this video here.